We present learning geometric-aware properties in 2D representation using lightweight CAD models or zero-real 3D pairs, a novel approach for learning 2D representation for object understanding tasks, such as semantic or instance segmentation and object detection, by providing better understanding of the underlying geometry and spatial relationships referred to as 3D pairs. Prior work such as Pry 3D relies on 3D scene scans, which are hard to obtain and not very diverse, making it hard to generalize. Instead, we use CAD models, which are lightweight and publicly available. Our key idea is to learn a joint embedding space of images and their corresponding CAD models with a geometric similarity score known as chamfer distance. We outperform to the only baselines like SimClear and MAE and are competitive to the SOTA that uses 3D scenes on semantic segmentation. Furthermore, our method can be trained on pseudo-pairs by predicting CAD models from images, allowing much larger training data than competitors. And that is a quick preview of our work. Now, let's dive into a detailed presentation. For 2D understanding tasks, like semantic segmentation, a common practice to leverage large unlabeled data is to borrow a self-supervised pre-trained 2D encoder and train a task-specific decoder. These 2D encoders can be learned with techniques such as SimClear, which learns to maximize the similarity between two augmented views of an image, or masked autoencoders, which learn to predict masked out parts of an image. However, the resulting representations often lack geometric awareness as the training only involves single views or simple augmentations like flip and crop. This can lead to poor results, especially on unseen views in downstream tasks. To address this, recent work called Pry 3D by Ho et al. Introduced a method to share 3D pairs with 2D representations using contrastive learning between multi-view images and 3D scene scans. While effective, this approach requires 3D scenes, which are often limited in size and variations. Our paper then investigates whether other forms of 3D data that are lighter and easier to obtain can also provide effective 3D pairs for 2D representations. Our findings demonstrate that CAD models can provide such pairs and serve as an attractive option instead of using a scene scan. Our approach can enhance the performance of 2D-only methods based on both ResNet architecture like SimClear and Vision Transformer like Dino and MAE on 4 common object understanding tasks spanning 6 datasets. Moreover, we achieve comparable results to state-of-the-art approaches that require 3D scene scans while using only lightweight 3D data. The key idea of our approach is to use CAD models to induce geometric awareness in 2D representations. We achieve this by learning a joint 2D 3D space of RGB images and point cloud versions of CAD models, which helps group images with the same CAD model together. Additionally, we use a geometric-based similarity score called chamfer distance to bring pairs with similar shapes closer together while pulling apart those with dissimilar shapes. This results in a geometric-aware latent space useful for downstream tasks. To learn this space, we employ 3 contrastive loss functions. The first loss constructs a geometric-aware space by selecting positives based on point clouds with the lowest chamfer distances for each batch member. The second loss function utilizes the same principle as SimClear, aiming to learn useful visual representation between different augmentations of images. Finally, the last loss function aligns the features from the first 2 losses, combining both 2D and 3D information. This results in a feature vector with both geometric and visual prior knowledge. Another key benefit of using CAD models is the ability to use pseudo-generated CAD models instead of the real ones. By leveraging existing works such as RGB CAD retrieval framework or 3D reconstruction from a single image approaches, we can construct a dataset of pseudo-RGB CAD pairs for training our method. This trick allows us to have more training pairs than other 2D 3D cross-model learning approaches. In our work, we used Loga from Gumeli et al. To generate such pseudo-pairs. Our fine-tuning results demonstrate improved performance on 4 standard datasets in semantic segmentation tasks. Training on pseudo-RGB CAD pairs enhances MIOU for 2D-only methods on either LaceNet or Vision Transformer architectures, while training on real pairs also achieves competitive results compared to the current state-of-the-art methods trained on scene scans. The qualitative results also reflect the improved performance. Two variations of our method, shown in the rightmost columns, can understand objects under challenging lighting conditions or uniform colors and textures. Furthermore, we constructed a pseudo dataset that is 6 times larger than the real dataset we used earlier. This leads to significant improvements in fine-tuning results. We can finally beat the state-of-the-art without using any real pairs in this setting. In addition, we also conducted fine-tuning experiments in other tasks. We beat the state-of-the-art methods in our setting on instant segmentation and object detection tasks in NYUV2, indoor COCO, and outdoor COCO, and show a recall improvement in object retrieval tasks in Pix 3D. Please see our paper for more details. In conclusion, our approach offers a novel and effective way to learn 2D representation with geometric pairs from CAD models. Despite being lightweight, CAD models help achieve similar improvements to existing approaches that use 3D scene scans. CAD models can be synthetically paired with images, allowing us to induce geometric awareness in 2D representation without requiring any real 3D pairs. Thank you for listening. If you would like to learn more about our work, including the full paper and source code, please visit our website.